Hello, this is Itsu. Okay, I've got my switching board here, and I built two channels, one on the right and one on the left. The two in the middle are still not occupied. And I have as a load this automotive bulb, two of them. These are 12 volts, 5 watts bulbs, and they do not have any filament which is curled up like this one, which is a curled filament which contains inductance. So this one does not have. So we have a fairly induction free, only resistant load to the MOSFETs. MOSFETs are IRF 260s and not that important. I made two channels, one according to the specs on the thread, and the other one I have made some modifications which should make it somewhat cleaner, I guess. I will mention them later. I drive the both inputs with my two-channel function generator. Both 100 kHz square wave, 4 volts DC. And 20% duty cycle. I have 6 volts on the input from my power supply here, 6 volts, and it's pulling 290 milliamps, and the bulbs are running on 20 volts, 130 milliamps, and the other one as well. So they have different voltages to minimize the crosstalk. Okay, 6 volt input being rectified by the 5 volts here, and I have one input probe, one probe, the purple probe, measuring the input of one device of the normal device, the left device, and I have the yellow probe on the output across the bulb, across the drain and the bulb, and the same of the other channel with the blue probe. So this is what we can see here. I have the purple trace is the input from the function generator for channel 1, and this belongs to the output of channel, the yellow channel, the upper channel. You can see it being pulled down from 20 volts. And we see a slight ringing on both channels. These are somewhat offset to see it better, but we have a peak there when the MOSFET closes, and the yellow trace is somewhat higher than the blue trace. You can see that here also. It's 1 volt higher or something, and that's, I think, because of one of the modifications I made. I have with the other scope also probing the gates of the MOSFETs, also the yellow probe on the channel 1 and the blue probe on the other channel 4, and these are on the other scope. And we also can see here that the blue channel is somewhat cleaner, somewhat straighter than the yellow, which has already a higher steeper. The blue channel is steeper than this one. This is already topped off. Oops. And the Miller plateau is clearly visible on the channel 1 and somewhat smaller here, so this is one of the improvements, I guess. But overall this is a nice, I guess, signal, but we are only at 100 kilohertz. If I now increase the frequency, first on, what are we, channel 1, going to 500 kilohertz, and now on channel 2, 500 kilohertz. We can see that the signal gets somewhat unstable, and also we can see here the gate signal. Oops. Sorry for the glare. The blue channel is somewhat stable, more stable than the yellow channel, because it's slightly better, I guess. If I now increase to 1 megahertz, sorry, we also notice then that the current being drawn by this circuit is going way up, still 6 volts, but almost 1 amp now, just by increasing the frequency. Okay, so we now can see that the signals are more rounded off. The blue channel is somewhat more squarey than the yellow signal, and the gate signals have to increase a little bit. Now gets also a little bit distorted both. The Miller plateau is much stronger here than here, and it's getting smelly a little bit. There's some things getting warmer, I guess. 27 degrees. The chip, the MOSFET driver chip, is 33. This one 39, so the channel 1 is getting somewhat warmer than the channel 2. Okay, well, what did I change? I'm not sure if it's visible, but here we have the MOSFET driver. This is the decoupling across the voltage, 100 nanofarad. And on this one I put a 49 or 47 micro farad tantalum cap to act as a buffer, and I put the decoupling cap directly across the plus and the minus of the chip, instead of further away, to minimize ringing. Also here I have used the normal diode and the 1 ohm resistor, and here this is for the MOSFET closing, and this is for the MOSFET opening. This is a 10 ohm resistor. I changed it here to a somewhat faster Schottky diode. This is also a Schottky diode. This is a little bit faster Schottky diode, but this is a 0 ohm resistance, so it's a wire. So I removed the 1 ohm resistor, and this is a 4.7 ohm resistor for the turn on time. And together with this buffer providing faster loading of the gate capacitance for faster switching on and switching off. The diode across the drain and the gate here is a MUR 460, which is a faster one than the original one, and what is it, 54 and 08 or something. So these are some slight modifications which I guess work better when doing higher speed. But overall this is a nice thing. When we change the load from a resistive load to a more inductive load, then we get a very fast increase in the spike here. Even with this bulb already I have here something like 200 volts spike for this little inductance for this bulb. So if you have a coil over there as a load, then you probably need to have some snubbering, because otherwise you will quickly overload the MOSFET and burn some holes in it internally after it breaks down. Okay, this is what I have found at the moment on this PCB. Thank you for watching.